Good afternoon. My name is Russ Sloboda. I work for Nelson Labs. I'm a toxicologist, and I've been working on many different medical device tox risk assessments, applying the new ISO 10993-17 over the last few months. And I'm here to talk about approaches that achieved favorable outcomes from extractable studies and tox risk assessment with this new standard. I had some involvement in developing that standard through the AMI group, and that has led to some good insights into what we can do and can't do for a successful outcome. After ISO 10993-17 was published in September 2023, it was recognized by the FDA in December, about 4 months later. As a consequence of many changes to the methodology in that standard and the normative criteria, new strategies for risk mitigation were needed to achieve a favorable outcome in a tox risk assessment, or TRA, of medical devices. And while that standard on the surface looks more conservative and stringent in some respects, our recent experience has shown several effective strategies that can be applied to achieve favorable margins of safety. And I'm going to get into some case studies of those applications. A small disclaimer, while those case studies follow the principles in the standard, in some instances, of course, as in all toxicology, you have to apply professional judgment and augment or interpret those concepts. So it's cautioned that regulatory feedback can vary among reviewers or in different jurisdictions. The basic outline of the study, which I'm going to go through for the different slides, is some of the more effective approaches include use of a toxicological screening limit that can dramatically reduce how many chemicals can be assessed in the risk assessment, eliminating many. Application of tiered contact or release duration categories to calculating a patient estimated exposure dose. Along with that comes the tiered default uncertainty categories, and application of release duration to case studies with total quantity extraction. In addition, the standard makes good use of release kinetics data, which are individual sequential extractions, and there's a release duration applied to those studies for risk assessment as well. In addition, the threshold of toxicological concern has remained largely unchanged, but some indications seem that it's time to stratify the TTCs by the exposure duration, and I'm going to talk about that experience. Next thing, lines of evidence-based approaches, which is stated in the standard for cancer risk assessment, and I have some case studies of that and discussion of some common metals that under some conditions could be associated with threshold mechanism of carcinogenicity. I have a case study that because the standard requires looking at not just one data point of one tox study, but the available breadth of the literature for a chemical, you have to look at a variety of no effect levels from different studies and how to select the best one. In addition, there are cases where the standard says you should sum the chemicals for exposure before assessing risk within a chemical class that have a common mode of action. And then lastly, in interpreting the mechanism of action and the endpoints for studies, sometimes you have to look at adaptive versus adverse effects and maybe rat-specific diseases to focus on your pathology to get the best outcome. I'm sorry here, I jumped ahead just a little bit. There we go. The toxicological screening limit being the first discussion point here. It's a tiered numeric screening criteria that's used to eliminate chemicals. There's a whole bunch of limitations. Most people have practiced those by now. We can only do this with identified compounds. You can't screen out chemicals this way for unidentified or unknown peaks. You can't screen out chemicals that are cohorts. You should always look into those more carefully. Cohorts of concern are in M7 and 21726, and compounds of very high potency, which FDA has given private feedback that that is not appropriate, that if they think it's high potency, they may say, please evaluate this even if it's below. It cannot be used to assess exposures and risks to infants. They've redefined that with an amendment to the standard. Infants are now defined as less than 1 year old, so that you'll have to assess all the chemicals. TSL cannot be used for volatile compounds coming out of inhalation or breathing gas medical devices. That's covered by a different standard. And also, the basic framework of the TSL, before I get into the example, is there are two TSLs, one for less than 30 days, up to 30 days of exposure, and one for longer than 30 days. And you must assess each category if your device clinical use could extend from, 1 day all the way up to long term. And it happens that the TTC is multiplied by the shortest release duration in that category, and that leaves you with two TSLs, 120 and 600. Practically speaking, the 120 is what matters because it's the more stringent to being able to use this TSL streamlining. Here's a case study of how dramatic it is. Here's a case, and very typical, we see a lot of these, a permanent implant assessed using TSL approach. We saw 90 to 95% reduction in how many chemicals have to have a full tox risk assessment. There were 40 compounds screened out, listed as less than TSL in that table. Only 3 chemicals highlighted in yellow that had to be require an in-depth tox risk assessment. Now, emphasizing that to use this, it has to be a total quantity extraction, and total quantity usually means exhaustive. So in this implant, it was tested with exhaustive extraction for chemistry. That's why we're allowed to use the TSL. There we go. Okay, the next concept I've introduced here, because it affects which direction the risk assessment goes, is there's a concept of estimated exposure dose and different case studies depending on how you estimated it. If you did a total quantity extraction for your chemistry, that's the blue graph on the left, you essentially continued the extraction down to the point where almost everything comes out, and the area under the curve in yellow is the total amount. That's the amount you detect. Under a release kinetics extraction, you're going to use 24-hour extractions sequentially from your device and get an analysis of each point, and you take the maximum or the highest 24-hour quantity, figure of merit, to assess the risk as a daily exposure, and emphasizing that's the units of a tox comparison is a daily exposure. And you can see that the one on the left is a great over-exaggeration, and on the right, it's more realistic. With the TQ extraction, an efficient worst-case assessment, which can streamline your work, is use a single EEDmax value, and that's the estimated exposure dose, divided by the body weight, divided by the shortest release of 1 day, in case it all comes out in 1 day. And that's the most conservative estimate of exposure compared to the most conservative estimate of toxicity, and see how that compares. And the most conservative would be a chronic tolerable intake. In the following slide, case studies are used to illustrate examples of this tiered approach and how we would mitigate risk. I'm going to cover this only very briefly. There's uncertainty factors that align with these different release duration categories. So if you were assessing the short exposure interval and you were using a subacute 28-day rat study, you derive a tolerable intake or allowable limit without any extra uncertainty factor to account for extrapolating from a study of one length to a clinical exposure of a different length. However, if you're going to use that short-term study to assess the long exposure beyond 30 days, like for a permanent implant, you have to use an extra safety factor of 10, because maybe that long-term exposure is more toxic than a short-term exposure at the same dose. So you can see with this example on the right, typical, just conceptually, you can see that the tolerable intake is very high for the short-term exposure, and then it becomes 10 times more stringent to assess the 31 to 365 days. And inversely, the estimated exposure dose is divided by a larger and larger denominator as you go down to longer durations, because you're distributing that dose, the total quantity, distributed into 1 day of exposure, or distributing it into 2 days exposure, or distributing it into 31 days of exposure, and hence often those two effects cancel each other out. And there's other uncertainty factors which I'm probably not going to go into detail, just to say that There are default values, and we have to be wary of those because you can't deviate unless you justify it. If a subchronic study is applied to chronic, you have a factor of 6 extra uncertainty. Subacute to chronic, it's a factor of 10. And there are a few others like oral bioavailability. All of those animal studies are oral studies 90% of the time. And as such, if a compound has high uptake from the gastrointestinal tract, you might be able to use a value of 1. No uncertainty for that being a true systemic dose to compare to an implant that's systemically exposing the patient. Other cases where you have low absorption, you might have a factor of 10 or more. Okay. Case study number 1, and I don't want you to have to squint your eyes because I'm just going to emphasize the points in red on this graph. The streamlined approach here, and many of the case studies we do, everyday jobs are this way. 90% of the chemicals, you do the worst case estimated in the exposure, and then you compare to the worst case, most stringent tolerable intake, and usually that passes. So 90% of your chemicals are taken care of with a single row of a risk assessment. However, this is a typical example of every now and then you get a margin of safety less than 1 by doing that worst case compared to worst case. And the step you're supposed to do then is to break out the exposure into the 4 intervals. I'm only showing 3 of them because beyond 365 days, it just gets, no matter what, it's going to get to a higher margin of safety, so it's going to look better. But the idea there is that you can see that this does pass when you break out the same data set. It's that same 960 microgram from an exhaustive extraction. For the 1-day exposure, you divide it by 1, but you don't have as stringent of a tolerable intake because you're using the short-term study without any extra adjustments. And so that passes in 2 to 30 days, you're dividing by 2. Again, it passes even better. And the longer term, 31 days and longer, you're dividing by the shortest release that could happen would be 31 days. So you distribute that exposure of 960 over dividing by 31, and it comes out to be a low number, and the tolerable intake, even though it's more stringent, it still passes even better. So that's a pretty typical way this happens. About 10%, 5% of the compounds will have a more nuanced calculation. Case number 2 comes out the exact same way, and for redundancy, I probably don't even need to cover it, but you can see it worked the same way. The margin is slightly below 1. When we break out the calculation, it does pass, and you can see we have 2 different tolerable intakes in that calculation. One's applied to the longer term exposure beyond 31 days or longer, and the other is applied to the subacute. It's all based on the same subacute study. And I just want to point out, sometimes you can actually find 2 good studies that addressed all endpoints, and maybe the 28-day study actually shows you that it's not as toxic. You might have a no effect level of 500, and the 2-year study might show a no effect level at 50. And so you could actually plug in different data for this stratification of the margin of safety. There we go. Okay, the next aspect here is instead of using total quantity data, you have different chemistry data. Now you did these 24-hour extractions. You don't have the total exhaustive amount. So instead of assuming what the release duration is, 1 day, 2 days, or 31 days, you actually measured the release at each time point. So you can take each value, you assess your 1-day exposure using a true 24-hour extraction, and you assess the remaining exposures up to 30 days using the highest of any of the other 24-hour data points. And that also gets you a lot of benefit for assessing risk, and there are other advantages as well. And I want to raise the awareness in the general community that historically the total amount detected in an exhaustive extraction was conservatively assumed to be released as a worst case estimate of daily exposure. That's an extreme overestimation of exposure and risk. These sequential 24-hour extractions, and they go under a couple different names. They could be called release kinetics, or they could be called simulated use. They provide a refined estimate, lower and more realistic. And as mentioned in 10.993.18, which is the chemistry guideline, information on the release kinetics of extracted chemicals can be helpful to support the risk assessment. Exhaustive extractions often are required by FDA as the first step, but the additional chemical characterization using release kinetics and simulated use extraction on only certain analytical tests that were a problem. Those can mitigate your risk, and they can be conducted concurrently to save time or sequentially. Now, I would not recommend people just skip the exhaustive on an implant, or you'll get in trouble with FDA going directly to release kinetics. They want to see what happened and how much you saw and what it was before you can do the second step of a release kinetics. In Europe, you might be able to write a rationale. I've seen that done quite successfully. So there's a little different in regulators on different sides of the pond here. Here's a release kinetics study number 1, and it emphasizes that you can actually use different animal studies or different toxicological endpoints for these different categories. So this was a case involving a European submission where cobalt was detected, and unfortunately, despite the fact that there's epidemiology data showing cobalt really doesn't cause cancer statistically in thousands and thousands of implants, they still insist that it's categorized under the REACH registration as a restricted substance. If it's above 0.1%, you have to do an assessment of the different types of risk, and you have to assess carcinogenicity. So 3 different endpoints apply to cobalt. One is cancer, one is reproductive, and the third one is, of course, the normal systemic non-cancer toxicity. So you actually have to assess all 3 of those when you do a cobalt risk and you know your device is going to Europe. The cancer, as you might expect, is the most stringent because there's oftentimes a very low threshold. And 1.1 microgram per kilogram per day is the daily exposure that we derived, and I'll show that later. And that carcinogen exposure assessment is more relevant for long-term exposures than it is to an acute or bolus exposure, because it's a cumulative thing that matters whether you exceeded the threshold. So we can exclude that stringent cancer assessment on just a single day 1 value from the first time point. The other aspect, which I'll cover later, is that cobalt has a threshold mechanism of action, which is actually even more favorable. It's not one of these assumption of worst case, linear, extrapolate, lower and lower, all the way down to the predicted safe level of 1 in 100,000 probability of cancer, which frequently is problematic for some chemicals. But this one is a threshold carcinogen, evidence for not being a risk below a certain level. Additional endpoints are the systemic toxicity, which is 5.4. That's much more liberal. And the reproductive developmental, which is 2.3. Interestingly, though, there's also a caveat. The repro developmental point of departure is associated with decreased spermatogenesis, and that is not considered an acute effect according to the according to the literature. The literature says that that effect was not seen except in chronic exposure. So when we go down to assess the indifferent data points, the laboratory in our Leuven laboratory did 10 data points to assure that they captured the complete release. The first data point was assessing the 0 to 1 day category, and that compared to the systemic threshold of 5.4 passes. And then the 2 to 30 day data points, we take the worst of them. So there's data points on day 2 all the way up to day 10. The highest is 44 on day 2. And the cancer TI is more stringent than the reproductive, so that's the most critical value to compare to. That also passes. So you can see using different studies or different endpoints can be effective with this release kinetics. The second study here is something only people in orthopedics might be aware of. Acrylic bone cements are used to permanently affix implants. Methyl methacrylate is a liquid monomer that's mixed by the surgeon minutes before application and during the surgery to fix a prosthesis and an implant. But because it's polymerizing in situ, it releases a huge amount of residual monomer until it's all cured, okay? And so ASTM has a procedure that requires essentially a more detailed release kinetics, 3 to 5 minutes extraction, 5 to 9, 9 to 15, etc. and you can add all of those extractions that are done on a curing glob of cement in a vial, and measure the total monomer released. They require triplicate time points because you can imagine you're doing live bench chemistry on the patient, and there's a lot of variability. So you need to look at more than one experiment and take a maximum for worst case. And then there's also a need to do the long-term exposure to the residual monomer, which is of course much lower, but you take partially cured cement and then you extract it for an hour, 24 hours, 72, and 168. And again, you can use the worst case for the long-term exposure to the residual monomer. And then after implantation, the rapid leaching occurs only for a few minutes. There's a half-life of 5 minutes in the blood. The concentrations in the serum peak after only 3 minutes, and it metabolizes very, very quickly. So basically it justifies using two separate values. To assess the acute and subacute exposures, we use a 9 to 14 day study in rats and mice, and that had pretty lenient no effect level. It gave us a tolerable intake of 1,700 for adults and 1,300 for adolescent. And to assess chronic exposure, we used a 2-year rat study. So that has a more stringent value. But in both cases, using these data sets of release kinetics, it passed. Okay, so the next thing is a little bit controversial. It's called the threshold of toxicological concern. It's been around for a very long time. In 2019, an ISO group came and borrowed the pharma requirements for TTCs for chemicals with no known value for carcinogenicity or for unknown chemicals. The TTC is a level of exposure to any constituent below which there should be no appreciable risk to human health for a particular type of exposure. Well, the type that's relevant to this TTC here is the most conservative, which is genotoxicity, the most sensitive endpoint. And so ICHM 7 and 21726 were designed to be protective for mutagenicity and carcinogenicity no matter what. They looked at the universe of the range of potencies of different chemicals and said a daily exposure for 10 years to lifetime, a 1.5 microgram will handle a level of safety for almost any carcinogen. There's a couple exclusions in there like nitrosamines, but for the most part you are allowed to do this if you don't think those excluded chemicals are in your material of construction. But there's also a more lenient value. If it's a device only used up to 30 days, it's 120 micrograms per day. Again, it's because of the concept that there's an inherent assumption that there's a linear dependence of the cancer risk on cumulative exposure, so there's a dependence of the threshold that's safe depending on how many days that exposure could happen. So that hence the tiered categories. However, even though you're supposed to use a 1.5 for any device that's long-term, if leachable release tapers off monotonically, and that almost always happens like with metal because there's no way for the organic chemical to be absorbed into the metal, it just generally come off in a day or two. If it's tapering off, a slight exceedance of this 1.5 is very unlikely to be consequential to a risk because you couldn't possibly have greater than 1.5 every day for over 10 years. So at least one manufacturer recently indicated that regulators have accepted a tiered TTC approach for unknowns as illustrated in the example. So this is not in the guideline, but we're starting to hear wins that people have done this. So I wouldn't try this at home because without some knowledge that it's going to work, I could be giving my customer a regulatory risk. However, I'm listening to that feedback and seeing where it goes right now. It may change the way we do this. As you can see, though, a value of 1.6 on the first unknown on the first row of that table, if you use that release duration principle, divided the 2-day exposure by 2, divided by the 31 to 365 exposure by 31, and so forth, you can see it would pass the 120, it would pass the for less than 24 hours or up to 30 days, and then the 1 to 12 month TDC of 20, a little less stringent, it passes that when you divide it by 31. So you can see that this is a mitigation strategy, and some of our clients have said they have tried it. Lines of evidence-based approach to cancer risk or best practices. Because 1099317, there's a section C.3.1. It states that mechanistic data can be useful in a weight of evidence assessment to establish cancers is associated with a specified exposure that is nonlinear threshold, or if it's a linear extrapolation. This makes a lot of difference in how stringent that comparison of to the one extractable in your data set that might be a carcinogen. And they give you a little bit of information on key characteristics. That's a concept coming from EPA a few years back. Oxidative stress, chronic inflammation, pre-neoplastic changes, proliferation of tissue, modulation of receptor-mediated effect. All of those can sometimes result in a threshold below which there's no effect. And there's ICH M7 as well as FDA guidance for industry for M7 that addresses mutagenic impurities with evidence for a threshold. So there's some basis for it. I've used it, both FDA and Europe. And there's a way to calculate it. There's an ECA guideline for that, as well as M7 has an example. It's basically an uncertainty factor approach as opposed to a linear extrapolation. Here's a case study on cobalt, which was that example we had before. It's an important metal because it's used a lot in orthopedic, very strong material. Good history of use. A threshold model of carcinogenicity has been cited in the literature. Like several other metals, it has been shown to generally be carcinogenic only for chronic inhalation exposure. The proposed mechanisms involve inflammatory reactions, which is an immune response. It leads to macrophages coming to the site, signaling, generating reactive oxygen species as a result of that reaction. And in those cases, oftentimes repeated high-level exposures can lead to proliferation, tissue hyperplasia, and tumor formation. So that's kind of like a classic pattern for some of these chemicals that are threshold carcinogens. Not all, but some. And the cobalt calculation, that's how we ended up with the 1.1 microgram per kilogram per day. The tox profile for that shows, despite it being a mutagen, and that's well documented, all these lines of evidence talk about the type of mechanism showing reactive oxygen species in a Fenton type reaction, reduced glutathione levels, increased oxidative glutathione activation of a monophosphate shunt pathway, and free radical induced DNA damage. So that was considered a threshold mechanism. We used a study, animal study, with 36% of animals getting fibrosarcomas from a 19-day repeated dose injection. And you use that with some extra uncertainty factors to calculate a NOAEL. The bright line approach by ECA was that if you have 36% cancer incidence as your LOAEL, you have an extra uncertainty factor of 36. Essentially what that, and an extra uncertainty factor of 10 for cancer being a more severe effect. And so essentially it's almost as if you're extrapolating down to a 0.1 incidence rate for the perceived threshold. Other metals, and there's varying lines of evidence. Most cases, only one of these metals will ever be assessed in a risk assessment, calculating an allowable intake for cancer. And that would be the special case of chromium, because chromium, the either hexavalent or trivalent chromium, have different toxicities. The IARC has classified hexavalent as well as US EPA and the World Health Organization as a known human carcinogen, but they have not classified trivalent. It's orders of magnitude lower potential for carcinogenicity. So chromium normally in a medical device is not in that form because it's a less stable form in the environment, and unless you have a weird synthesis reaction going on for a novel material, sometimes it might happen with a pharmaceutical. But most medical devices will be assumed to be trivalent, and protective level can be calculated in the case where it's hexavalent that deals with the possible carcinogenicity. On the opposite extreme, you have aluminum. It's a household item. It's generally considered safe. Nobody has classified it as a carcinogen, but there have been some in vitro and in vivo studies that suggest a potential for genotoxic effects, such as micronuclei, even though most of those mutagenicity tests were negative, like the Ames test. But it was found that this happened when cells are exposed to higher concentrations of aluminum ions. And if you look at whether that could be clinically relevant, based on the existing weight of evidence, that wouldn't be possible to have those high of a concentrations of aluminum ion in the human body. So it's not classified as a carcinogen, even though there's some evidence. Antimony and nickel are kind of in between. Trivalent antimony has been shown to have in vitro genotoxicity in some mammalian systems, but both trivalent and pentavalent are generally negative in any of the non-mammalian, like the Ames test with bacteria. Chromosome aberration for antimony have been inconsistent. IARC has classified it as possibly carcinogenic to humans, and the cancer mechanism of action for antimony is thought to include production of reactive oxygen species and indirect interference with DNA repair. There's been a recent review, several, in fact, of antimony studies finding evidence of indirect mechanisms of action, possibly including these reactive oxygen species that could exhibit thresholds as a function of the antioxidant defenses. The homeostasis in the cell allows certain antioxidants to be compensated so that they don't have deleterious effects, and hence you don't get this proliferation of cell response and immune reaction if you're below the level at which the homeostasis can handle that oxidation. So the authors concluded those effects are probably have thresholds, and it's likely that they could establish such a threshold if needed for antimony. To this date, I have not yet seen a paper giving you a study which you can hang a number for a point of departure for a threshold allowable limit for antimony. Most of the regulators are only saying ignore carcinogenicity. We're just going to look at systemic toxicity. Now, if you were in a different industry like occupational health, that would not necessarily work because a lot of these metals can be carcinogens by chronic inhalation exposure, and that's where you do overload the physical processes of homeostasis. Nickel is a known genotoxin. Nickel and nickel compounds are classified by IARC as carcinogenic to humans. The mechanisms have been reviewed. Generally, the genotoxic agent is a +2 valence state, but direct reaction to divalent nickel with DNA may not be relevant under realistic exposure conditions. In other words, only under very high exposures that are not clinically relevant. Nickel is also a redox active metal that can catalyze Fenton-type reactions and thus generate reactive oxygen species. And again, the same mechanisms would apply there. So these effects are likely due to indirect mechanisms, and I have not seen regulators ask for nickel to be assessed for carcinogenicity for this reason. Okay, so that one was pretty far into the weeds. Whoops. But these are kind of fun aspects of, here we go. The next aspect is because the new standard says you must assess the breadth of the toxicological data in the literature for each chemical, you can't just cherry pick one study, and you need to look at point of departure sometimes on overall evidence from several studies. So how do you do that? Because now we have to document that. It's required that we document the profile of a chemical with each study that could be relevant and why we selected one of those studies. So this is a good example, tetramethylsuccinonitrile. Nitriles have been studied in vivo and in vitro. The primary mechanism for many of them is related to the production of cyanide ions, and those interfere cytochrome C oxidase in the electron transfer chain, disrupt aerobic respiration and production of ATP. But interestingly, this particular steric hindrance with the extramethyl groups on tetramethylsuccinonitrile was shown not to produce cyanide metabolites as compared to an unsubstituted succinonitrile. Okay, so there were 5 studies that I had to look at. How do I select the right point of departure for the tolerable intake for an acceptable outcome? General idea is you pick the highest of the different no effect levels, but below the lowest low effect level, provided those studies have relevance to humans. So in this case, the first study had among the highest doses 1, 3, and 10 milligram per kilogram per day. They're all 90-day studies too. At the high dose, there was reduced body weight, increased absolute relative liver weight, and enlarged hepatocytes in the central lobular or mid-zonal regions of the liver. However, It's cautioned that treatment-related increases in liver weight can result from a variety of causes. Sometimes they're due to damage to the liver, and other times they may not be. Hepatocellular hypertrophy can reflect a natural adaptive response, in some cases from the metabolism of xenobiotics, which are within the liver's capacity to maintain homeostasis, especially if the observer liver effects such as enlargement might be reversible after a recovery period. In addition to the treatment-related effects, there was a renal nephrosis only in male but not female rats. And that's another special consideration. Classic male rat-specific disease is seen with degeneration of proximal tubules in the kidney, hyaline droplet formation in the cytoplasm of epithelial cells. To talk about that later, but that effect is not relevant because it's, again, specific to male rats. It doesn't happen in humans. Second 90-day study, they looked at lower doses, 0.1, 0.31, and they didn't see any liver effects. They only saw kidney effects. Third 90-day study, they looked even lower, and they finally found a NOAEL below 0.1, and again, only saw kidney effects at the highest dose. In the fourth study, they looked at dogs. Well, dogs aren't susceptible to this liver-specific disease in male rats, and they dosed them at 0.1, 1, or 3. Not as high as the first study in rats, though. No effects in the kidney. We're seen at any dose level, which corroborates this interpretation that that alpha-2 globulin is a male rat-specific disease. There were no microscopic histological effects in the liver or kidney here, and it confirms that the liver is not a target organ in dogs. Lastly, there was a 90-day drinking water study where they administered 7.5 milligram per kilogram per day to rats. Focusing on the changes to the liver, there were no histopathological findings. So essentially, given the overall weight of evidence, looking at all of these studies, the liver and the kidney were examined, and the kidney effects were attributable to that alpha-2 globulin, a male rat-specific disease with no relevance to humans, pointing to the liver for the point of departure for what tox value to use. The highest no effect level was 7.5, and that's below the lowest low effect level of 10. That's the value you want to pick, provided all studies are equally representative. Next, part 17 now says we should sum toxicities, or sum the chemicals and then compare to a toxicity. Has guidance in Annex E, also in Section 9. When two or more constituents elicit the same harm, two chemicals causing the same harm at the same target organ, and have the same tolerable intake, we should be summing the chemical exposures before we compare to the allowable limit. Under Section 9.2.2, they say two or more constituents shall be summed when each constituent could affect the same harm in the same target organ and have the same mode of action. That alludes to maybe two different chemicals that are unrelated to each other because they both have the exact same mechanism should be summed. And in that case, you don't just sum the values, you have to sum the margins because they may each have a different threshold, and it's a margin of safety is the reciprocal of the sum of the reciprocals of each chemical. In some cases, a distinct mode of action is not evident. This is your caveat that you don't have to sum everything. If we had to sum everything that affected the liver, all kinds of devices would fail. But if we don't have any evidence on the mode of action, we don't have to combine disparate chemicals together for assessing risk. Now, here are the probably some of the most common things that are summed together. Obviously, if something differs by the number of carbons, 4, 5, 6, 7, sometimes you can sum those and say they have the same mode of action. Caution that you need to do a robust evaluation for the class, if that's how you're going to assess the toxicity, and make sure you pick a conservative number that does apply to all of the members of the class. Sometimes it's very obvious what those classes are, other times not so obvious. For example, the very short chain alkanes may have some different types of toxicity, like hexane is neurotoxic and forms certain metabolites, that don't happen in the longer chain alkanes. So some of the shorter chain alkanes are assessed discretely. The things that sometimes aren't even apparently the same class turn out to be able to be added together. The antioxidants like Ergonox 1076, you might group them with hydrolysis and oxidation byproducts as these occur in vivo. And here's an example. Ergonox 1010 is a phenolic antioxidant. It's added to polymers as a stabilizer to protect against thermooxidative degradation over time. It's widely used, FDA approved as an indirect food additive in packaging. Since the hydrolysis of that ester bond in this antioxidant occurs readily in aqueous systems, the degradants shown, and there's quite a large family here, they're all expected metabolites and therefore would be expected to have similar toxicity because they're going to be oxidized in vivo as well. And you're exposed to the parent, you'll be exposed to all of them as it gets metabolized. And so hence we add those concentrations up. It's good to have a tox risk assessor that knows that these things all belong to the same antioxidant class. The last part I'm going to get into here is it's into the weeds, but again, because we now have to describe the toxicological endpoint, what is the harm, and understand the mechanism of action of that harm, we're now looking at not just reach your hand into the box and pick a no effect level and just run with it. We're now looking at the nuances of those studies, and a lot of times that information is in the pathology summary, what histopathology found. So I'm going to show you 3 of the most common things to watch out for that a good toxicologist will take an in-depth look and not a superficial look. Hepatocyte hypertrophy is perhaps the most common finding that's identified as adaptive in non-clinical toxicology. Hypertrophy is not considered a direct toxic effect when the severity is low and it's not accompanied by hepatocyte degeneration or cytotoxicity. Well, how would you know that? Well, you look at all those study details. Because the treatment-related increase in liver weight can be a variety of causes, you look for correlative histopathology changes like inflammation, necrosis, degeneration, or elevated enzyme activity biomarkers for the liver like ALT, AST, ALP, or bilirubin. Hepatocellular toxicity in the absence of those things may reflect a natural adaptive response from the metabolism of xenobiotics, which are within the liver's capacity to maintain homeostasis, especially if those effects, such as enlargement, are shown to be reversible after recovery. So hence, you may not have to call, that might be that you might have a no effect level, but that's not a no adverse effect level. And we're really talking about adverse effects to assess toxicity and derive an allowable limit. Alpha-2 globulin nephropathy is a unique male rat-specific disease. A lot of chemicals trigger this. It's characterized by the accumulation of hyaline protein droplets in the proximal tubule of the male rat kidney. While this disease is not seen in female rats or in test species like mice or dogs or non-human primates, an inexperienced study director might interpret those findings as adverse. In such cases, let's look and see if there's other studies on the same chemical and see if a different pathologist doing another study was able to determine that they're not adverse, and you can use that overall weight of evidence. Rodent forestomach tumors are another area that can go either way. In this case, you got to be careful. You don't want to overlook something, but there are some that are not relevant. Rodent tumors that are caused through genotoxic mechanisms involve cell proliferation and genetic changes in oncogenes and tumor suppressor genes. Chemicals that are DNA reactive and cause tumors at multiple sites in the body, in addition to the forestomach, are likely to be relevant human carcinogens. You think about why is forestomach a problem in rats? Well, often it's gavage dosing through a tube, and the rats have a unique organ, forestomach. It's easily irritated because a gavage tube inserted is constantly exposed over and over to a repeated dose of a chemical. And chemicals that act through non-mutagenic mechanisms produce chronic inflammation or local irritation of the forestomach, and that can lead to continuous induction of cell proliferation attempting to compensate hyperplasia and ultimately carcinomas. So if the chemical was dosed above the maximum tolerable dose, MTD, in a cancer bioassay, that wouldn't be relevant for humans. Chemicals that induce tumors, though, in multiple tissues are more likely to be relevant. And the last thing I want to say is that there are some literature citations. If you want a copy of this, you can have it. That determination of a NOAEL is complex because it depends on correlated dose response changes. A lot of times clinical changes alone aren't relevant. Hematology, serum chemistry, urinalysis, you don't adopt a NOAEL from that alone, but they may be supporting other effects such as co-occurrence alongside morphological lesions or clinical signs. Okay, so the key takeaways ending this presentation: after FDA recognizes this revised international standard in December, we've gained a lot of practical experience applying it to various categories of medical devices. The updated standard is no longer one size fits all, just pick a NOAEL and do one calculation. There's a lot of detail that has to be provided. Certain strategies have been discovered that are highly effective at achieving favorable outcomes. These strategies, which I've just covered: tiered contact duration RD categories to scale the exposure to the proper duration, picking the relevant animal studies from several to align with the corresponding clinical exposure duration, adopting uncertainty factors similarly, which appropriate for that exposure duration, applying release kinetic studies for individual extraction time points to align with those exposure categories, summing compounds that belong to the same chemical class that have a common mode of action, using lines of evidence to assess something that's a carcinogen, defining point of departures that as a conservative NOAEL that's the highest of several different study NOAELs but below the lowest low effect level. And then lastly, focusing on pathology, pathological interpretation of adaptive versus adverse effects and rat-specific diseases. So by adhering to these principles, together with having a well-documented toxicity profile for each chemical that meets the data collection requirements of this new standard, it will ensure best practices, transparency, and in the majority of cases, a favorable margin of safety and regulatory acceptance. Okay, that's it, and I'm open for questions for just a couple minutes here. Go ahead. I don't. Yes, I can. Right. Um, yes, the question was, have we submitted to regulators use of release kinetics for the different strategies? Um, First of all, the case study that I showed was for cobalt. That was a nuance because it has different endpoints. And I would have to say that that is going to FDA next month, okay? That case study, though, is predicated on the principles that I've used many times. Those three toxicity values, one for repro, one for carcinogen, and one for systemic tox for cobalt. That's probably been submitted 30 times between Europe and FDA, and they've never objected to having those particular values derived for cobalt. Now, as far as the release kinetics concept itself, well before the new standard, we have used release kinetics data, and it frankly is optimal for a study that fails the first time. And there's a couple of reasons, and I'll tell you why. You're not over exaggerating cumulative extraction and calling it a daily exposure. Secondly, for an identified compound, that 24-hour highest exposure will pass. Now, using this approach, it's clearly stated in the standard that you look at the 0 to 1 day separately from the 2 to 30 day, and release kinetics, you can take the highest of data point 2 all the way to the last data point from extraction as for the second category. That approach has probably zero chance of being rejected because that's real clear. Um, the concept of unknowns are another story. And what I have found in practice is that if you can show the unknown is tapering off on release kinetics and it drops to below whatever the longest term that's applicable to the unknown. So permanent implant, it has to get below 1.5 so that you can prove that the average over the entire lifetime cannot be over 1.5 microgram per day exposure. So if the last time point falls below 1.5, the first few you're going to be able to justify. Now, how you do that is up to debate, and I usually just a written explanation has been acceptable for that situation, and it's all based on, do you add up enough exposure to exceed a carcinogen cumulative dose? So that gives you two very, very useful reasons why it's worthwhile if your chemistry and exhaustive study failed, even though FDA said try that first. Certain risk, like sometimes these high toxicity values, isocyanates, phthalates, very stringent thresholds. When you go to that release kinetics, you're going to lower the temperature and you're going to say, I'm doing 24-hour data points. Less is extracted each 24 hours. And by combining those approaches, you come up with an effective approach that very often does pass because there's several variables that are more realistic when you do it that way.
Yeah, it will be acceptable, yeah, if you have performed release kinetics study. But if you have not performed, then, for example, for NBR study, we used to have, I mean, still do, like first iterations is 72 hours.
Right.
So if you divide that 72 by 3 to derive for daily exposure, so I think that's the concept maybe for you use for assumed release kinetics. So you're dividing by certain days to get your daily release. Has you ever applied those for regulatory submission, and what's your thoughts?
The question, if I understood correctly, is whether 72-hour intervals instead of 24-hour intervals could be used in a regulatory submission, and taking a 72-hour interval dividing by 3.
Right.
3 to 5 years ago, or actually 4 to 6 years ago, that used to be sometimes accepted reviewer-specific judgment. We started to see a lot of pushback around 2019 that no, you don't know for sure that it all didn't come out in one day instead of spread evenly over the 3 days. You might be, by taking the average dividing by 3, you might be underestimating the actual exposure, and hence we have stopped doing that, both where I'm working now and where I worked before at Johnson & Johnson. We generally then only take the 24-hour amount, or we use the extracted amount, the total, as if it's a daily dose. Occasionally, like I say, we'll try to make a statement about, the nature of the material. So an example is these stringent thresholds for TTC apply to organic chemicals, not to metals. And if you have a metallic device, it's non-porous, it doesn't absorb chemicals. It's any residues of organics are on the surface. They should come off within a few hours or a day or two. And in those cases, you can have a rationale that says, well, we're slightly over that 1.5, but because this was an exhaustive extraction and because it's a non-porous metal, there's no mechanism for this to be released slowly. It should deplete. It's slightly above in the first extraction. That should be pretty much all of it. It'll be below over the long term for daily release because it doesn't have an available pool to leach. So those are, I guess, a hybrid approach of a rationale combined with the TTC concept.
So yeah, I have many questions, but this is the last one. For release kinetics, I think still we are developing. It's not solid yet. How should we perform? Yeah, we know we need to do time interval. That's great. If we need it, we can do it. So, for example, permanent implant, it requires extraction for utilizing GCMS, LCMS, and based on the material, it can be ICP and or maybe IC. So, from your experience or your judgment, do you think we need when you do a release kinetics, you do NBR, one instrument, targeted analysis, or you should do all? What's your thoughts on that?
Release kinetics is going to be more expensive. You might have 4 GCMS instead of 1. 24 hours, 48, 72, 96, a lot more expensive. We only do it where we have to. Usually the exhaustive extraction works just fine for the mild solvent. Water, it works for usually midpolar isopropanol. It doesn't work for hexane. Now, the hexane is only applied to GC and LC. That's where we would do it, just for that. Now, when we do it though, we already did the exhaustive data. We have hexane data. It just maybe it doesn't pass, or maybe it didn't meet AET, depending on what kind of problem the hexane caused with the interaction of the material, right? They want to see the data, at least in FDA they do. So if we have done the exhaustive already, in the release kinetics, you don't have to take it all the way out to exhaustivity.